Hello there, everybody. Welcome back. This is lesson 2 in Unit 1, the atom, and today's topic is atomic history. So in our last video, we talked about, atomic structure, how to read the different element squares on the periodic table, how to calculate the number of protons, neutrons, and electrons in any given atom. So today, we're going to cover thousands and thousands and thousands of years of atomic history. Okay. So as you probably guessed, the model of an atom has changed pretty drastically over, these 6 models that we're going to talk about today. And the first model was developed thousands and thousands of years ago. And the model that we use today hasn't even been around for 100 years. So it kind of puts things into perspective a little bit. Let's kind of dive back in time and look into the different models of the atom. So let's travel back to ancient Greece, where this dude named Democritus is studying the atom. So what he said in about between 460 and 370 BC, so literally over 2,000 years ago, he said the atom is the smallest piece that any substance can be broken into, and there are these tiny, indivisible, indestructible particles that he called atoms. So everything was made up of indestructible spheres, and he called them atomos. Now, all said and good, let's fast forward a couple thousand years. So now it's about 1808, and John Dalton comes into play. And he's like, atom hasn't been studied in a long time. Let me see what I can contribute to, this knowledge. And so he agreed with Democritus, and they both said, elements are composed of these tiny particles called atoms. Now, what John Dalton added is that all atoms in elements are identical. So let's say all hydrogen atoms are the same. So if you look at a hydrogen atom here, where you are in a different country, all hydrogen atoms look the same. And he said also that these different elements had different atoms. So a hydrogen atom is different or not equal to, let's say, an oxygen atom. Every element has their own specific, unique atom. And when we talked about atomic structure, which one of the particles kind of identified the element? So which particle, the electron, the proton, or the neutron, told you what element it was? Again, that is the proton. The proton, or the atomic number, that tells you what element it is. That's specific to each individual element. Okay, so let's keep going. Fast forward even further. Now it's 1904, and we're talking about this dude named J.J. Thompson. So he's like, okay, what can I contribute to atomic history? And what he discovers are electrons, using his cathode ray tube. So we're not going to spend that much time going to the cathode tube ray, but it's kind of important to mention his model. And so in 1904, he's like, the atom is mostly positive, this positive thing with these negative electrons stuck in it. And he was like, oh my god, this looks just like the plum pudding model. Or it looks just like plum pudding. And so plum pudding was a very popular dessert in 1900s. But nobody knows what that is anymore. So I like to call it the chocolate chip cookie model. So if you think about a chocolate chip cookie, you have, your cookie. And what Thompson said, that cookie, that part is positive. But then you have these chocolate chips inside it that is kind of stuck. So the whole cookie itself is positive. But you have these negative electrons stuck sporadically in the cookie. And so that's what J.J. Thompson said. The atom is positively charged with these negative electrons stuck throughout it. So as you can see now, we have a positive part and we have a negative part. That's more than we had in the last model, but that's still not what we use today. So let's kind of keep going. Okay. Our next dude, his name is Lord Ernest Rutherford. And so he's most famous for his gold foil experiment. We're going to dive deeper really into what this actually is. But basically what he did, he hung up this piece of gold foil in his lab and then bombarded or kind of shot these positive alpha particles at it. And I'll show you this setup in a minute. And basically what his conclusion was is that the atom is mostly empty space with a small, dense, positively charged nucleus. So again, let's think back to our atomic structure, the structure that we talked about yesterday. What is in the center of our atom, or the nucleus of our atom? So you should have said protons and neutrons. So these neutral things are the neutrons, and these positive things are the protons. There's no R there. Protons. And then the model we looked at yesterday had these electrons kind of floating around. So even with this picture, you can see that the center is positive, because remember, protons are positive, neutrons are neutral. The protons cancel out the neutral, so it's all positive. And then most of the space was empty. So with the gold foil experiment, he had two major observations. One, again, that most of these alpha particles, or these positive things, passed right through the foil. And that means that the other few particles were deflected. And what deflected means, it kind of hit something and then bounces off. So if I was to deflect off of this, it hit and would bounce off. But he's saying most of the particles went right through. So with those two observations, we know that the atom is mostly empty space, and the atom has small, dense, positive centers, or nucleuses. So here's what his setup looks like. Here is where he shot out his alpha particles, and so they're going towards the gold foil. Now most of them pass straight through, but every so often one of them would hit something and bounce off in a different way. And so that's kind of what this is showing here. These alpha particles, most of them pass right through, but every once in a while you get one that hits perfectly on that nucleus and shoots it a different way. Now the reason we know the nucleus is positive is because these alpha particles are positive and the nucleus is positive. So if you think about magnets, when two things that are the same come together, they repel each other. So the positive alpha particle and the positive nucleus, they come together and then they repel each other and bounce off. And that's how he knew the nucleus was positive. If the nucleus was negative, that would have meant the alpha particle would have gotten stuck to the nucleus. So again, gold foil experiment, atom is mostly empty space with a small, dense, positive center. Okay. Now, it's 1913, and this dude named Niels Bohr comes into play. And what he contributed is he said, well, electrons exist, we already know that, but they exist in these well-defined paths called orbits. So if you think about, our solar system, you have the sun, and then, here's Earth, and it just goes around in its orbit. And then you have all the other planets. So that's why this one is called the planetary model. So these well-defined orbits. So in terms of our atom, here's your nucleus, and these electrons follow this perfect path, this perfect circle. And he said, well, there are different shells or orbits, and that each orbit had a different amount of energy. So let me draw this neater. There would be one shell, there would be two shells, there would be three shells. And the farther away you are from the nucleus, the more energy you have, or the more energy the electron would have. So the way I like to think about this, if, this is you. Now, you are responsible for babysitting this child. Now, if this child had a low amount of energy, let's just say it does exist. People put their kids on a leash. So, you're holding this child, you're going to, let's say, the zoo. This child is calm. So, the calm child is near you, it's close to you. You don't mind being near the calm child. But, after, a long day at the zoo, you get ice cream and candy because, why not? So now, here is you. The child is now over there. Here's your child. The child ate so much candy, and there's that leash. Now the kid has so much more energy. The kid's just running around crazy. So, just like an electron, the higher energy that kid had, the farther it ran away from you. The calmer the kid, the less energetic, the closer it is to you. If you think about it like this, and we're going to spend more time on this tomorrow. If, Halloween's coming up, if you go trick-or-treating, eat a bunch of candy, you're going to get super hyper. Your family, your friends might say, okay, now that you're in this high energetic state, go somewhere else, get far away from me, and when you calm down, you can come back. So that's kind of what Niels Bohr said. These electrons have different amounts of energy, and the farther away you are from the nucleus, the more energy that electron actually had. Okay. Lastly is this dude named Erwin Schrödinger, and he is known for the wave mechanical model. So he said, I agree with everything so far that, what's his name? That Bohr said, but instead of these perfect orbits, the electrons exist more in these electron clouds, or orbitals. And these orbitals were the most probable location of an atom. So here's, your nucleus. And let's just pretend we're taking a picture of an atom every, second. There's an electron. It just there is a picture on a picture on a picture. And, each dot represents a location where the electron is. Now, yes, there are some, dots that aren't totally in line. But generally, you could say the electrons will most likely be in this green area. And that is what an orbital is, the most probable location of an electron. Okay, so this kind of sums everything up. If we look at John Dalton, he said one of his positives was that atoms were different from other elements, but he didn't talk about the subatomic particles. Move over to J.J. Thompson. J.J. Thompson realized, electrons are existing, but he didn't explain the nucleus aspect of the atom. Rutherford comes along and says, hey, we got a positive center in the nucleus. Electrons don't exist, but he didn't explain why those electrons actually go around the nucleus. Fast forward, Niels Bohr started talking about how these electrons are organized by energy levels, but he's missing about these energy shifts, and we're going to spend time on that tomorrow. So, lastly, the Schrödinger model. He said, electrons don't move around in orbits, but they're in a probable location. So we have an idea of where they'll be, but, not exactly. And this is kind of what we use today. So as of 1926, this is the model of the atom that we use today. Okay, so that's it. Next time, we'll talk about average atomic mass and where the mass on the periodic table comes from. Bye.